Okay, so today we're going to start a discussion that will last for at least a couple of lectures. Yes? Okay, fine. Yes, question.
In the last lecture,
Yep.
we filled the gap for atoms in the just the valence electrons in the
S state, yes.
How can we fill for atoms the valence electrons in the p state?
Okay, so the question is how do we fill the states if there are electrons in the p states or so. To some extent, this distinction between S, P is irrelevant once you move to the band structure. The band structure is something that where you essentially, well, you might be using ideas from atomic physics if you want to build the band structure. For example, if you use the model that we use so far of the one-dimensional chain of hydrogen atoms, we build this linear combination of atomic orbitals and all that. But in principle, for example, the model we're going to discuss today, and for the next two lectures, which is the free or quasi-free electron model, doesn't know anything about the atomic properties. It assumes, I mean, you don't need to know anything about the atomic properties. The only thing you need to know, of course, is the number of electrons that you have available, that you need to place in your band structure. All right? So whether you start from atomic levels or from a completely different approximations like we'll do today in order to build your band structure, the way you fill it only depends on the number of electrons that you have available. In the valence band, of course, because you assume that the core states can be forgotten. They are down, down, down in energy. Okay? And they're all filled, of course. Okay? So you only need to know the number of valence electrons, total number of valence electrons in the unit cell in order to be able to fill the band. You don't need to know whether they're S or P or whatever. You just need to know the total number of electrons. Of course, in order to determine the band structure, you may wish to take advantage of the atomic properties of your system, like we did for the hydrogen chain. Right? We used explicitly the fact that there was a 1s orbital. We constructed a solution in terms of linear combination of 1s orbital. So we used the information from the atomic state. In the problem we're going to discuss now, we don't even want to know about the atomic problem. We will want to know it only later on when we're going to fill the resulting band structure. Then we need to know how many electrons we have in the unit cell in order to fill it. Okay? Yes?
Can I have a crystal for atoms which are inert or no?
Sure, why not? I mean, crystals of argon exist, of xenon exist. Helium is a bit rare. As you probably know, helium, you cool it down and it becomes a fluid at some point, and a superfluid at some point, but it never crystallizes. Helium, for some reason, is the only element that, whatever is the temperature, it doesn't crystallize at ambient pressure, at least. It remains, it goes into this superfluid phase, and it never crystallizes. If you apply pressure, if you squeeze it, actually, it has also a solid phase, a crystalline phase. So you can think of crystals made of rare gases. They exist, even xenon. I mean, larger rare gases do have also crystal solids at ambient conditions if you lower the temperature sufficiently, if you go, sufficiently low in temperature. There's conceptually no difference with respect to other solids because you still have a number of valence electrons. The question probably there is whether you want to consider your electrons are core, all core and no valence, or if you want to introduce some valence, right? Because inert atoms clearly are such that even what you might be calling valence electrons are so tightly bound to the nucleus that they don't really interact with the nearby electrons. If you take this assumption that they're all core states, you're left with just with the atomic levels, and that's it, which is not a bad approximation. If you look at the band structure of, say, xenon or argon, it will consist of very narrow bands. I hope it is clear by now that, for example, if you think of the discussion we made for the hydrogen chain of hydrogen atoms, that if the interaction between the two atoms is very weak, all our delta E and T are going to be small, and so the width of the band is very narrow. In principle, if it's 0, it becomes the atomic-like levels. So for a rare gas, solids made of rare gases, it's up to you. I mean, either you assume that there is no interaction at all, and therefore you live with your atomic levels, or you assume that there is a small interaction, and then you have a band that has a width which is very, very small. The bandwidth, I guess, for argon is much less than an electron volt. I think it's a fraction of 0.2, 0.3 electron volts of width, right, compared to energy differences between atomic states of several electron volts. So it's really almost like a delta function, I mean, a constant, if you look at it in terms of K. So it depends. I mean, if you, I mean, that's a very good point, however. These are systems which are really at the borderline. You may think of them as just as collections of atoms. You may not really need to bother about the formation of a band in those cases. Okay, but here we are in the opposite limit now. Now, the model we are going to discuss, actually, I'm going to start with the simplest model, which is the free electron model. So this is a very extreme approximation that we're going to make. In fact, the free electron model is even too extreme for a number of properties, with a few exceptions. What does it mean that we are dealing with a free electron model? It simply means that our Hamiltonian, which you remember we wrote in this way with V periodic function, we still assume that there is an underlying Bravais lattice, that the atoms are placed in crystalline positions, but we assume that the electrons don't see the nuclei. So that this potential doesn't exist, or it's 0, or a constant, even better, because a constant is the same. So in other words, the electrons, even though there are nuclei sitting on well-defined crystalline positions, we make the approximations that the electrons don't see these nuclei. So first, I mean, this is a bit puzzling because, right? I mean, you're used to think, at least so far, we've been used to think in terms of electrons being first belonging to atoms, and then we built wave functions, a linear combination of atomic orbitals. So in some sense, I mean, we've always assumed so far that electrons see the nuclei. Actually, they see them heavily because we are starting from the atomic solutions. So the Coulomb potential is there if we want to start from the atomic solutions. Here we're taking a completely different approach. We're going to the opposite extreme. We're saying the nuclei are there, but the electrons don't see the nuclei. When is this a good approximation from a physical point of view? Well, there are systems. In fact, let me give you an example. The first column of the periodic table. Sodium, lithium, potassium, rubidium, first column. Here you have one electron. The wave function of that electron is very delocalized, because that electron is typically the first electron of the next principal quantum number. Right? So if you are, I hope you're familiar with the periodic table to the extent that you, I guess, know that for the first column of the periodic table, you're filling the first electron in the ns with the ns electronic configuration, and all the n-1 configurations are filled. So this electron is essentially alone and is very delocalized with respect to all the other electrons that are in the atom. So when you put together a crystal of atoms composed of atoms of the elements of the first column of the periodic table, you have a situation in which if this is the crystal and these are the position of the nuclei, the wave function of the ns, the last electron for this particular atom, if you forget about the existence of the other ones, just the atomic wave function, is something that extends very long distances from this, comparable, if not longer, than the distance between atoms in the crystal. Okay? This is because essentially the interaction between the atoms is dominated by all the other electrons, and only this one is delocalized. All the other ones are very localized. So the atoms are allowed to get closer than the size of the last only unique electron that you are left in the ns orbital. That means the other one here will have an ns, will have a wave function which extends also over perhaps distances which are comparable, if not longer, than the distances between atoms in the crystal. You may recall that this is exactly the opposite of the approximation we've assumed in the model that we built for the hydrogen chain. In the hydrogen chain, we're assuming that the wave functions were very localized, right, to the extent that we could only retain, we were only forced to retain only nearest neighbors overlaps, because we are assuming that the wave functions were going down very fast. Now, this is really a completely opposite extreme. The wave function of the atom is totally delocalized, and it delocalizes over one or more lattice spaces, distances between atoms. So it is clear that the atomic picture for this wave function is a completely wrong starting point. Because if we started to use the atomic picture to describe our electronic states, we have to consider the overlap of this with the next one, but also with the next one, and with the next one, and with several others. So we wouldn't be able to truncate our expansion only to the first shell of nearest neighbors. Okay? Similarly, so this is the first argument that essentially is telling us that there's no way we can start a discussion starting from the same approximations we have used before. Similarly, this cloud, this electronic cloud, because it is very delocalized, it is very easy to polarize. You can change the shape of this electronic orbital very easily because it is very weakly attached to its own nucleus. So this electron is, well, in fact, you probably know that the ionization potential of atoms in the first column of the periodic table is very low. It's very easy to ionize, to strip the electron away from those atoms. They are very delocalized. They are very shallow in energy if you look at just the properties of the nucleus. So they're very easily displaced in some sense. If there is a perturbation, immediately this electronic cloud will respond to that perturbation. What does it mean, this extreme capability of these electronic states to respond to external perturbation means something for our discussion about electron-electron interactions. You remember that towards the beginning of our classes, we discussed that electron-electron interactions are important. We were going to neglect them throughout our course, but there are cases in which we need to introduce it qualitatively, and this is an example. If you are this electron here, the electron sitting centered at this point, that is this circle here, you will certainly see the presence of the other nuclei, but at the same time, all the other electrons, because they're so easy to polarize, to displace their charge, will actually screen very efficiently all the other nuclei from your view. Okay, so you're here, you see the nuclei, but at the same time, all the other electrons will adjust themselves in order to screen the strength of the Coulomb potential coming from the other nuclei. They're very polarizable. They're very easy to distort their charge, and therefore they are very effective in reducing the strength of the nuclear potential, the attractive nuclear potential due to the other nuclei. Okay? So there are both aspects. The delocalization and therefore the fact that there is a large overlap between wave functions, which is such that we certainly cannot start from an atomic picture. Connected to that, of course, is the fact that these systems have a very low ionization potential, which means that the electrons can be stripped away from their nuclei with very little energy. And connected to that is also the fact that these electronic clouds are very polarizable, very easy to distort, and therefore that nuclei, let's say, the nuclei that each electron sees, their interaction is going to be screened very effectively by the presence of the other electrons. So electron-electron interactions play an important role here, even though, of course, we're not going to study it in any further detail. But for example, what used to be our starting point for V, which was the sum of Coulomb potentials centered at different sites, we're going to assume that it's going to be completely screened away by the other electrons. Okay? So that's the spirit of this approximation. All the other electrons are so efficient in screening away the presence of the nuclei that we start from the assumption that each electron sees nothing. It sees just a constant potential. There's no nuclei. It doesn't see the nuclei. So there is a crystal, but each electron sees just a flat potential, constant or zero, because a constant arbitrary additive constant doesn't really change anything. So that's the physical, reasoning that brings us to the free electron model. Of course, we will immediately see that this model is so extreme that it explains only very few properties of these crystals. We need to go a little bit beyond that. But let me first solve this problem. Right? This is a very simple problem. It's trivial to solve. In fact, you already know the solution to this problem, right? This is an Hamiltonian, free electron. What are the solutions to this Hamiltonian? Plane waves, right? So clearly, solutions of the form e to the I q dot r, these are solutions to our problem. The potential is zero. So therefore, this is a good solution to the problem. Yes?
How much is the length scale to take account when we for the approximation to be good?
This is almost never a good approximation. It's really an extreme case that allows us to say something. I would say as soon as the extension of the wave function becomes comparable to the distances between atoms, comparable, not several times longer than that, but comparable, then this approximation starts to be a good starting point to understand at least qualitatively. If you're dealing with rare gases, inert gases, this is clearly, you will see that the extension of the wave function is a small fraction of the distance between. Okay, so you're in the completely opposite approximation. Say this approximation gives qualitatively interesting. There is another reason why, I'll show you to you later, but there is another point that we need to understand, and we will actually see that this theory is a bit more robust than it looks, but it will become clearer later on. Okay? For the time being, let me just take it as a very extreme case, very trivial to solve, because if V equals to 0, we know the solutions to the problem. We know their energy. We know everything about the free electron problem. Now, in principle, the problem would be over, right? It's solved. We know the energies. We know the wave functions. We know everything about it. In fact, we want to go a little bit beyond that. We want to, at some point, we will have to modify this model to introduce a little bit of V. In principle, this model doesn't even need to know that there is an underlying crystal, if you think about it. Right? These solutions don't even know that there is a crystal underneath, because if V is 0, the nuclei are completely decoupled. They're not even there in the picture. As far as the electrons are concerned, there is not even need to introduce the presence of the nuclei if V is 0, of course. Plane waves, period. Now, we are going to introduce the presence of the nuclei in the next step. So what I'm going to do now is to discuss the solutions of this problem, which we know very well, in terms assuming that there is actually an underlying lattice. Okay? What does it mean? It means that Bloch's theorem has to apply. Bloch's theorem with this periodicity has to apply. Now, if V is periodic, the solutions must obey Bloch's theorem. V equals to 0 is periodic and has the periodicity of this Bravais lattice, right? Constant. Why not? Of course, it has many more symmetries. It has a continuum. It has a continuous symmetry. But in addition to that, it also has the discrete symmetry of the lattice. So in principle, solutions of the problem with V equals to 0 must obey Bloch's theorem also for, in principle, for any Bravais lattice, in particular for the one that we're dealing with. Okay, so suppose we are in a Bravais lattice here, that the potential is 0, and now we're going to classify the solutions of the free electron problem according to Bloch's theorem with this Bravais lattice. We can do that, right? Because a constant potential is a periodic potential, so it must satisfy Bloch's theorem. So let me remind what Bloch's theorem states. It says that solutions of the problem can be written in this form. Uk of r equals to psi k of r, uk of r e to the I k dot r, with k belonging to the Brillouin zone of this particular Bravais lattice. So we have a Bravais lattice, we have a reciprocal lattice, we have a Brillouin zone, and there I can write solutions in this form. But my solutions are of this form. How can I translate and transform them in such a way that they look like this? Now, if I have a generic Q, suppose that I'm drawing things in 2 dimensions, right, just to simplify my notation. I have a generic Q in the 2-dimensional space. On top of this plot, I can superimpose my reciprocal lattice vectors. We are in reciprocal space, right, as far as Q is concerned. So I can just superimpose here. Suppose it's a square lattice. It will look something like this. These orange points are my reciprocal lattice vectors. Let me also draw the Brillouin zone. Right, that's the Brillouin zone of a square lattice. Now, it would be tempting to say, look, I just set U as a constant and Q equal to K. Right? An obvious way to write it in terms of Bloch's theorem is to say, look, I mean, U is a constant. I take K to be equal to Q. And this is of the Bloch's form. Well, there is a problem, however, because K needs to be within the Brillouin zone. And Q is an arbitrary vector, not necessarily within the Brillouin zone. So this argument actually works as long as Q is within the Brillouin zone. If Q is within the Brillouin zone, yes, I can say that U is a constant, 1, K is equal to Q, and I've been able to write e to the I QR in this form, with K belonging to the Brillouin zone, because Q belongs to the Brillouin zone. But this is trivial. Q can be an arbitrary vector, and for example, the way I draw it here is clearly not a vector of the Brillouin zone. But remember, we've done this trick several times now. If Q does not belong to the Brillouin zone, I can decompose it. I can decompose it into a vector, a G vector, plus a vector which belongs to the Brillouin zone. In this particular case, it will be, if I translate my Brillouin zone by this particular G vector, I can certainly write it as a combination of this G plus this this K. I can write my Q as a linear combination of G plus K. I just need to find the closest G vector to Q. I move first there with the reciprocal lattice vector, and then from this reciprocal lattice vector I move by within the Brillouin zone by an amount k. Okay, so here, if you allow me to use the colors here, this will be G, the orange vector, and this will be K, the vector within the Brillouin zone, right? And this decomposition is, by the way, unique. There's no other way to decompose it in any other form. And it is always possible. Okay? So it's unique and it's always possible. Whatever point I have in my space, I can always decompose it in a unique form as a reciprocal lattice vector plus a vector within the Brillouin zone. But now, if I use this assumption, if I use this statement, I can write e to the I qr as e to the I g dot r e to the I kr. Right? Where k belongs to the Brillouin zone and G is a reciprocal lattice vector. But if G is a reciprocal lattice vector, what can I say about this function? It's periodic, right? It's the same periodicity of the Bravais lattice. So in practice, I've written my wave function as a periodic part times a phase where K belongs to the Brillouin zone. Okay? So I have been able to write a generic plane wave into blocks form by extracting out the periodic part and the phase by just decomposing my vector Q in terms of the reciprocal lattice vector plus the vector inside the Brillouin zone. Okay. Now, let me use this side of the blackboard now to draw. I want to draw my band structure now. I know the solutions, I know the Brillouin zone, I know everything. Let me now do it. Let me now draw the band structure for a one-dimensional case. Okay, so in the one-dimensional case, everything becomes much simpler. The scalar products become just product between numbers. Reciprocal lattice vectors are 2 pi over a times n, an integer. Brillouin zone is minus pi over a to pi over a, right? So it's in one dimension, everything is trivial or very simple. So here I have my energy. This is pi over a. This is minus pi over a. And let me take an arbitrary value of k. Okay, I take an arbitrary k there. So I fix k in the Brillouin zone. I fix this k. Fixed. I'm looking for the solutions, precisely like I did last time. Okay, I fix k and I look for the solution. We need to solve our problem, but I mean, we don't need to solve anything because we've already solved the problem here. How many solutions do I have for a given k? For the free electron problem. I have an infinitely many values of q, right? Because all the possible solutions of the free electron problem are all possible values of q. Now I'm fixing k now. What am I left with? What can I change? The reciprocal lattice vector. So all the solutions for a given k correspond to all the possible reciprocal lattice vectors. Now, of course, it's a discrete number of the, well, it's infinite, but it's a discrete set. It's not a continuous set because I fix k. So the only thing I can vary now is g, and g can take any possible value of the reciprocal lattice. vectors. In one dimension, what are the possible values of G? In one dimension, the possible values of G are 2 pi over A times n. Right? So, in terms of energies, well, I never wrote the energies here, but obviously the energy here is h squared over 2m q squared, right? That's the energy. Which means the energy, if I write it in this form, will be h squared over 2m. Let me do it in one dimension, because I'm dealing with one dimension. G plus k squared. I'm removing the vectors because we're in one dimension. And G can take these values, 2 pi over A n. And I fix k. So k is fixed. So let me draw the solutions now on the blackboard. Let me start with G equals to 0, n equals to 0. The energy is h squared over 2m k squared. Okay? So k squared means that it's a parabola. Here you go. This one is n. Let me use the same notation that I'm using for the reciprocal lattice vectors. Corresponds to the n equals 0 reciprocal lattice vector. N equals to plus 1. N equals to plus 1 here becomes 2 pi over A plus k squared. If I have to draw it here, so n equals, so this is, let me do it. N equals 0, energy is equal to h squared over 2m k squared. N equals to 1, the energy is equal to h squared over 2m k, 2 pi over A plus k squared, right? So this is a parabola centered at minus 2 pi over A. So it's centered somewhere here. Parabola. Again, I'm not interested in what happens outside the Brillouin zone, because we've already made this argument, right? Whatever happens outside the Brillouin zone, there will be somewhere else in the Brillouin zone. So I don't need to care about solutions outside the Brillouin zone. So this is the n equals to 1 solution. Of course, it goes all the way up. And similarly, sorry, I forgot to mention that n equals to 0, k squared actually extends all the way also to negative numbers, right? Because this is a parabola also to negative numbers, n equals to 0. So it's all n equals to 0. What if I take n equals to 2? N equals to 2 becomes 4 pi over A. So it's a parabola centered, 2, 4 here. Well, it doesn't fit in the blackboard, right? Because the parabola centered here will cross the Brillouin zone very, very high in energy. So I can forget about, well, I cannot forget about it, but it's going to be outside the blackboard. N is not restricted to take only positive values. You can take also negative values. So n equal to minus 1, for example. N equals to minus 1. Energy is equal to h squared over 2m minus 2 pi over A plus k. Again a parabola, but now centered at 2 pi over A. Well, somewhere there, it will hit this point, hit here again. Notice that this parabola is exactly symmetric to this one, right? I'm just exchanging the k into minus k. So this is n equals to minus 1. N equals to minus 2, minus 4 pi over A plus k. Parabola centered at 4 pi over A shoots up Doesn't show up in this plot here. In principle, I can continue, right? I can continue 3, 4, -3, -4, and I will obtain a sequence of segments of parabolas whose energy is higher and higher and higher. In fact, it grows like n squared almost, right? At k equals to 0, this is n squared. So this point, for example, is actually n squared. N equals to 0 is 0, right? If I'm at k equals to 0, the energy is exactly g squared, if I'm at k equals to 0. So g squared is n squared. So the nth parabola will hit the origin, k equals to 0, at 0, 1, 4, 9, and so on and so forth, right? 16 and 27 and... Sorry, 25 and 36 and so on and so forth. It's segments of parabolas that are higher and higher energy. So in our language, in the language of Bloch's theorem, what we discussed last time, if I sit here at a given k, I will have this solution, another one corresponding to n equals to 1 further up. Then there will be another one corresponding to n equals to -2, then n plus 2, and so on and so forth. So I have a sequence of discrete levels for a given k. That's exactly what we argued would be the solution according to Bloch's theorem. Now we actually have the solutions for a very simple problem. Yes? Yep, that's interesting. Yes, we have a twofold degeneracy here. We have n equals to -1 and n equals to 1, which happen to be degenerate here. But we have another degeneracy here. N equals to 0 and n equals to -1 are degenerate here. So we have a degeneracy also here. This is a degeneracy, but this is exactly the same degeneracy, because this point is equal to this point. So it's physically, there's no difference between this degeneracy and this one here. But this is different from this one, and there will be an infinite number of degeneracy at all the, essentially, at the zone center, k equals to 0, and at plus pi over a or minus pi over a, which is the same, you will have only degeneracies for this particular model.
But in the last lectures, when we studied the bond structure,
there was no...
It's called at k equal to 0.
Yes. Yes. I mean, this is, depends on the model, of course. So in this particular case, there are degeneracies in these places. Okay. Oh, yes, very important. Let me discuss filling in this problem. Suppose I have 1 electron per cell. Well, 1 electron per cell, I know the recipe, right? I know that a full line here going all the way from here to here corresponds to 2 electrons per cell. That's the rule that we've been using, and it's actually exact, although we only proved it for 1 dimensions. So if we have 1 electron per cell, we will have to fill levels up to exactly 1/2 of the way here. Right? Because only in this case, there will be half of the full number of available states filled. So if the number of electrons per unit cell is 1, then these states will be filled and all the other ones will be empty. So there will be a Fermi level somewhere here. If I have 2 electrons per cell, I will have to fill completely the first band. That's actually quite interesting, because my Fermi level hits a degeneracy. That's quite an interesting statement, and we'll see the consequences in a moment for that. So this would be for a number of electrons per cell equals to 2, for example. 3, well, again, I have to fill completely this one, and I can start filling the second one. Notice that I always have to fill the lowest available states, right? So I cannot fill portions of parabolas that go straight up. I mean, I have to fill first this triangle. I have to really go up and then fill all the levels, right? So clearly, if n is equal to 3, well, then I will have to stop again exactly in the middle, so here, exactly in the middle of this segment, so here, and here there will be another Fermi level for number of electrons equals to 3, right? Four electrons per cell, okay, I can fill completely this lower band and this upper band here, made of two portions, this one and this one. So I will again hit a degeneracy for n equals to 4, for a number of electrons equals to 4. In fact, you obviously can conclude that if the number of electrons per cell is even, you will always hit a degeneracy, right? Either here or at the center, depending on whether it's, say, 2 or 2, 6, 10, so on, or it's 4, 8, 12, and so on and so forth. While if the number of electrons is odd, you will always cross the Fermi level at points where there is no degeneracy. Well, saying that there's no degeneracy is not completely true, because this is a degeneracy, right? This and this. Okay? So k minus k is a degeneracy. But that degeneracy is always there. It's not a real symmetry. Well, it is a real symmetry. In some sense, it comes from time reversal symmetry, which is true for all systems. The fact that when we take the complex conjugate of an Hamiltonian, we get the same solutions is a consequence of the fact that the Hamiltonian is Hermitian and real, and therefore there's no, it's an expression of time reversal, essentially. So this is somehow it's a trivial degeneracy in the sense that all systems have this degeneracy. It's not specific of a particular crystal, of a particular model. The k minus k degeneracy is always there. But I mean, there are aspects of this degeneracy that are actually important. And we'll see in a moment also why this degeneracy is less interesting than this one here. Okay. Good. Let me now discuss the properties in a bit more detail, the properties of systems with 1 electron per cell. Again, take all the elements of the periodic table. They can be described by FCC or BCC crystals, and they all bring 1 electron per unit cell to the valence. All the other ones are core states. Okay? So this situation is very common for electrons in the first row, first column of the periodic table. Sorry, I can go back here. I want to make some general statements because I can make general statements under the assumption that these systems can be described by a free electron model. The first obvious statement is that what is the value of the Fermi level with respect to the bottom of the band. Now, that's something that you can, in principle, measure experimentally, because you can measure the position of the lowest available state, the lowest, say, field state, and you can measure this width here. So if you decide to measure the Fermi energy with respect to the bottom of the band, you can make some statements about the height of the Fermi level with respect to the bottom of the band. Right? In 1 dimensions, for example, the length of this segment must be exactly half the full length of the Brillouin zone, because we argued that with 1 electron per cell, we need to fill exactly half of the available states. And the available states, you remember this gridding that we did at some point, right? They were in the limit of very large Born-Volk-Karman boundary conditions. They correspond to a very finely spaced set of grid points, equally spaced. So if we want to fill half of them, that corresponds to filling exactly half of the segment corresponding to the full Brillouin zone. So we can actually say for sure that with 1 electron per cell, the length of this segment is going to be pi over 2a, right? 1/2 of the, say, 1/4 of the Brillouin zone, or 1/2 of the distance between 0 and minus pi over a. Of course, the same is true on the other side. And because I know that this is a parabola, I can actually say that this is equal to, so the Fermi energy is equal to h squared over 2m pi over 2a squared, right? With respect to the bottom of the band, of course. This is true for any system with 1 electron per cell described with a free electron model. Actually, you can even introduce the density of electrons, which for a one-dimensional system, if you have 1 electron per cell, you can say that let me use n. The density of electrons in 1D at least, let me put 1D here, is 1 over A, right? It's 1 electron every A. It's the real space density of electrons. I have 1 electron every A, every unit cell. Now, the density in 1 dimension has the dimension of 1 over a length, right? In 3 dimensions, it's 1 over a length cube. In 1 dimension, it's 1 over a length. And since I have 1 electron per unit cell, the density of electrons is 1 over A. Notice that this is a constant density because our solutions are plane waves. So the square modulus of a plane wave is a constant, is 1, right? So it's a constant density. And we have 1 electron per cell. Notice that we don't have just one wave function. We have, in principle, an infinite set of wave functions. But all of them have this property. So for all of them, the wave function is a constant. So if I add up constants, I obtain a constant. And this constant, I know how to measure it because I know that I have 1 electron per cell. So if I did everything properly, the density must be 1 electron, 1 over A. I'm talking about number density, right? I'm not using rho. I don't know what kind of notation is used in general, but by n, I typically mean the number density, so the number of electrons per volume. Sometimes you may wish to use rho, the real density, but then density would be E over A. I mean, it depends on the notation, of course. This is the charge density, this is the number density, the number of electrons per. Let me use the number density, 1 electron per A. Which means for a one-dimensional system, yes?
One question.
Yeah.
Let's take a matter.
Sorry?
Okay, let's say an atom in the first column of the periodic table.
Yes.
And then let's say it crystallizes in the FCC.
It crystallizes in the FCC. Okay. Yeah.
How can I feel those?
Oh, now I'm going to do a three-dimensional system in a second.
Okay.
Let me finish the argument about the one-dimensional case. Okay? So in 1D, n is equal to this. So the Fermi energy is equal to pi squared over 4, which I can collect here into an 8, n squared. Right? Pi squared, n squared, 2 squared, 4 multiplied times 2, 8, 1 over a squared, n squared. Here. In fact, the result is even more general because, after all, this property cannot really depend on the fact that there is an underlying lattice. I mean, all this discussion, we are using the fact that there is an underlying to make our construct in terms of Bloch's theorem, so on and so forth. But after all, this is just a free electron model. So I can, in principle, get rid of the underlying lattice if I want to describe just the properties of the electrons. So this is to argue that this statement is valid also when the number of electrons is not 1 per cell. It's generally valid. There's no reason why the system should distinguish between 1, 2, or 3 electrons per cell as long as the electrons don't even know about the existence of an underlying lattice. What's the purpose of calling them 1 per cell, 2 per cell, if they don't know about the existence of a lattice? Okay? So I could, in principle, prove it also for 2 electrons per cell, 3 electrons per cell, and so on and so forth. I could redo the derivation. But what I'm arguing is that the result cannot change, cannot differ, because this result is entirely based on the behavior of the electrons. And the electrons don't even know about the existence of an underlying lattice. We force them here to know about it, but they don't know about it. We wanted them to learn about the existence of a lattice because we want to construct our states based on Bloch's theorem. We are somehow forcing the electrons to do something completely natural because they don't know about the existence of a lattice. They don't need to know about the existence of a lattice. So this is to say that this conclusion about the Fermi energy being given in terms of n squared, once I write it in terms of density, must be universal. Cannot depend specifically on. If you wish, I mean, we can actually just show it just qualitatively. Take 2 electrons per cell. The Fermi energy is here. Full segment. This is twice, so it's pi over a. Okay, so let me just redo it So for 2 electrons per cell, this would be pi over a. So there would be but at the same time, the density would be 2 over a, 2 electrons per cell. Okay? So if I remove the 2 here and I want to write in terms of n, I need to add the 2 again, so I go back to exactly the same relationship. Okay? So it doesn't change. If I change this into pi over a, and n becomes now 2 over a, if I want to insert n here, I need to add another 2, so I get exactly the same expression. Okay? But the point is actually deeper than that. The point is that electrons don't need to know about the existence of a lattice. So the results cannot depend on the fact that we're dealing with 1, 2, or 3 electrons per cell, because they don't need to know about the existence of cells. So this result is more general than that, than the 1 electron per cell. Yes? We are going to see the gaps forming in next lecture. That's a free electron model.
So that's the reason because there is
No gap, it's free electrons. In a free electron model, there is energies can take a continuum of possible values. Okay, so there should not be any gaps in the free electron model. We're going to introduce the gaps not today, but next lecture. Okay, give me 5 minutes, 5-10 minutes, and I'm done. I wanted to discuss now the two-dimensional case. We're getting to 3 dimensions, but let me start with the two-dimensional case. Okay, 2 dimensions, I need to make some drawings here. Most of our arguments continue to hold. I mean, until we add vectors, the arguments are valid. But at some point, for example, when we constructed this plot, we explicitly constructed it in terms of a one-dimensional system. So what if I have now a two-dimensional system? First of all, if I draw my energy, I have to draw it as a function of a two-dimensional set of possible values of k, right? So if I have my energy here, k, now I have to use the vector. Here I must have a two-dimensional possible set of possible k's, right? Because in 2 dimensions, E of k is defined on a Brillouin zone, which is a two-dimensional Brillouin zone. So let me now draw the Brillouin zone. I'm going to use the green. So if this is the value, say, of pi over a in the 2 dimensions, well, that will be okay. So this is 0 pi over a. This is pi over a 0. This is 0 minus pi over a. And this is minus pi over a 0, right? It's a square. Hopefully it looks like a square. Sorry, this is a bit odd. More like this. So it's a plane, and the Brillouin zone is a square. And there will be reciprocal lattice points, say, here. Of course, the origin. Of course, somewhere here. There will be another one here. They are at 2 pi over a, right? N and m. There will be one somewhere here. Another one here, and so on and so forth. These are the reciprocal lattice points. And if you remember, I mean, energy. I'm now rewriting the expression using vectors. Let's just follow the same arguments that we followed for a one-dimensional case. We fix k. The possible values of the energy correspond to all the possible g's, right, for a fixed value of k. So if I fix k in this plane, say here, for example, I will obtain values of the energy for all possible values of g, discrete numbers. But these objects here are parabolas centered at minus g. Okay? So essentially, what I have, instead of having a set of parabolas centered at 0, minus 2 pi over a, plus 2 pi over a, plus 4 pi over a, and so on and so forth, I have now a set of parabolas centered at all the reciprocal lattice points in 2 dimensions, right? The one at g will be centered at minus g, but essentially for every reciprocal lattice point, there will be a 2-dimensional parabola coming out of that, right? Like we had parabolas originating from all the reciprocal lattice points in 1 dimension. Okay, so just think of, don't ask me to draw it, please, because this is going to be very messy. But at each of these points, you're going to have a parabola sitting on the floor and starting from that point. Okay? Now, suppose that you are now in the vicinity of this point. Let's now reason in terms of this portion of the solutions. If I'm close to the origin, well, there will certainly be a parabola that goes here and here, right? There will be a parabola growing out of the origin. Well, and for a while, this will be the only solution inside the Brillouin zone, because all the other parabolas will start to enter in the Brillouin zone at much higher energies, like in the one-dimensional case. So let me assume now that I have 1 electron per cell again. 1 electron per cell means that I have to fill this parabola up, 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 up. And of course, when I fill this parabola, I'm correspondingly filling states which occupy a circle in the Brillouin zone, right? Every time I grow with my parabola and I fill states on this parabola, I'm essentially covering a number of states which grows like a circle inside the Brillouin zone from the center. So the number of states that I will be filled will correspond to a circle in the Brillouin zone. If I have filling increasing, 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 this circle will just expand. Where do I stop? It's important now to determine where I stop, because I want to determine the Fermi energy. Okay? I will have to stop when the number of electrons is over. And I have 1 electron per cell. That is, I need to fill half of the Brillouin zone. But the Brillouin zone is a square, and this is a circle. Right? And the circle grows, and I have to stop when the area of the circle is exactly 1/2 of the area of the square. Right? So when will I stop? Let me call this K the Fermi vector. So let me give it the name Kf. It's the vector where I have to stop. It's this vector, right? The analog of this vector here. So the condition will be that pi Kf squared, which is the area of that circle, is equal to the area of the whole Brillouin zone, which is 4 pi over a squared in 2 dimensions. Right? So Kf, actually, let me keep Kf squared. I don't really need to, 4 pi squared. A squared, so it's 4 pi over a squared. Why do I keep Kf squared? I don't even take the square root. Because when I want to calculate the height of the parabola at that point, from the ground, from the bottom, I just need k squared, right? It's h squared over 2m kf squared. So in 2 dimensions, the Fermi energy is h squared over 2m kf squared, or h squared over 2m 4 pi over a squared. There's a pi. Okay? Is this clear to everyone? We have to fill this parabola, right? So we increase the energy, and by increasing the energy, we are going to occupy a circle that is larger and larger and larger. As soon as we occupy all the points in this parabola, we are going to expand the circle. And we'll have to stop when the area of this circle here occupies exactly 1/2 of the total Brillouin zone. Oh, sorry. There's a factor of 2 here. It's just me 1/2. Here I fill the whole Brillouin zone, sorry. There's a factor of 1/2 here. 2 pi over a squared. Yes, sorry about that. So here it's 2 pi over a squared, which is h squared over m pi 1 over a squared. Any other mistake? So it's 1/2. That's very important. Because if 1 means that we're filling the whole Brillouin zone. Actually, it is impossible because I cannot, with a circle, occupy the full Brillouin zone. It's a square. So I can only do it if it's 1/2, by the way. All right, so it's 2. I hope I did everything correctly. Correct me if I'm wrong. So this is the value of the Fermi energy. Let me translate it into density. Now in 2 dimensions, density, if I have 1 electron per cell, is 1 over a squared. 1 electron over a unit cell, a squared. So the Fermi energy is h squared over m pi n. Interesting. It depends on the density now linearly, not like the square. And again, the result is, of course, more general than that, because the electrons don't know about the existence of the underlying lattice, so this result must be true regardless of what is the number of electrons per unit cell. Yes?
Shouldn't we change the definition of that density because this is now 2-dimensional?
Why not? This is a 2-dimensional density, right? Number per area. This is number of electrons per length, 1 dimension. This is number of electrons per area. And I have 1 electron in an area given by the unit cell, which is a squared. I'm using the number density, not the charge density. Charge density would be E over a squared. But here I'm using the number density, the number of electrons per cell. Okay, I think we can stop here.